I had a conflict this morning. Conflicted with me sleeping too much.
Yeah, that's what I thought. How much do you owe me? I literally said that I would.
Oh my god.
18 points?
Each?
Sweet.
Well, I asked you to do
And
something.
one's 12? Sweet.
It's just because there's, actually, you'll probably find this homework, we give it.
Sorry, I'm like.
Graduate students.
Short contact stars are usually 5.
This doesn't look nearly as bad as the last one.
5 or 3.
I just see 18 and
We just saw 18 and we're like, whoa.
Well, I figured out how many answers that you had to give for the problem. And I
Oh,
just
okay.
took n times
So is it like,
3.
okay,
Yeah.
sorry.
Right.
So, yeah, I mean, it's what we were
I
doing
mean,
in
18
class
does seem like kind of
yesterday.
a random number, right?
I'm good.
So-
real scared there.
So in those first two, I gave you some 5x5 matrices, and I'll outline what my expectations are on this. Find primary, or find the rational canonical form, primary rational canonical form, and Jordan form, if possible, for the following matrix, well, matrices, over Q and over the complex numbers. And of course, the Jordan form will always be possible over the complex numbers. And so, anyway, so as far as what you do, in fact, please do not submit 18 pages of you doing Gaussian elimination. Don't want it, don't want it. You owe me a bottle of aspirin and scotch if you do that to me,
I feel
right?
like if I do 18 pages of chapter, like someone shouldn't see it.
That's right, you have it right. So, but also don't just write the answers down, right? Just, so I'm okay with, so if I were doing this problem, what I would do is I would write the A minus lambda X form, and I will say, I used whatever I used. I did it by hand, I used MATLAB or Maple or whatever, and here's the Smith normal form. Now take that and do an interpretation and give me my answers there. That's, I don't need your Gaussian elimination or anything. If you want to do it by hand, good for you, may make you stronger, but I don't need to see it. Number 2, find all possible rational canonical forms for a matrix over R. That's the real part is a little bit important there. With characteristic polynomial, x cubed minus 1 quantity squared, right? So what do you know, by the way, the characteristic polynomial is this, what do you know about the size of the matrix? Yeah, it's going to be 6 by 6. This will be a 6 by 6 matrix. So I give you the characteristic polynomial. The characteristic polynomial is actually the product of the invariant factors or the product of the elementary divisors if you so desire. So this gives you some possibilities for what they could be, figure out what they all are. And I'm going to do a problem that smacks of this one. This is kind of going to be my last example for this, but I think this is a really nifty problem here. So what you have here is GL3Z2, which is 3 by 3 matrices over Z2. This is actually the second smallest non-abelian simple group, as a matter of fact, and it's got, I think, 168 elements in it. So here's another application of all this business with conjugacy classes and the canonical forms. Find the number of conjugacy classes and give me a representative for each conjugacy class in there, right? Like the class equation says that all 168 elements in here fit in some conjugacy class of different sizes, perhaps. Find all of them and give me a representative from each one of them, which is kind of a cool problem. Okay, any questions on that? Okay. So, my usual help couldn't be here today, so, oops. So I'm gonna be controlling the screen myself, so if there's any problems with me controlling the screen, you can ask for control out there. Oh, let me also say. And he is going to talk about spatial statistics today. It sounds like a really interesting talk, so I encourage you all to be there. Oh, I did do some scribblings here. So here's the example. GL so this is the set of just to be clear, A, B, C, D. Just 2x2 convertible matrices over C5. How many, by the way, just for giggles, how many of these matrices are there? They're not all invertible. Okay, I think I see where you're going with this. First row, how many ways can I fill in the first row? Right, but one of those is no good, right? Right, 24, right? Because I've got 25 choices for what goes in the first row, and 0, 0 is the only one that torpedoes me, right? If I put 0, 0, there's no way it's invertible, but anything else, you still got a chance, right? So now that I've made this choice in my first row, how many choices do I have in my second row? Well, all I need is for the rows to be linearly independent. And that is, I just need the second row to not be a scalar multiple of the first row. So I've got 25 possibilities, but take away the 5 multiples of this row and get 20. So there should be 480, which actually is 2 to the 5th plus 3 plus 5. Yes, yes. So, you know, you could ask yourself all kinds of things from like last semester about the CeeLo theorems. There's this big fat CeeLo 2 group of order 32. There's the CeeLo 3 group, the CeeLo 3 and 5 groups are all cyclic, and there's probably a ton of them, right? The question is, what are the conjugacy classes? Well, in fact, I don't even need the matrices to be invertible, but I'm going to specialize that since I'm looking at this group. Each matrix in GL2Z5 is conjugate to its rational canonical form, right? And so basically, and it's an if and only, right? So basically, the conjugacy classes conform to all the rational canonical forms that we can find, right? Everybody okay? So let's ask ourselves this: how can we do this? So many characteristic polynomials are possible? What do you think? Yeah, 2 by 2 matrices always have quadratic characteristic polynomials, right? So basically, when I do my thing, I'm going to get a quadratic polynomial. How many are possible? There's really only one restriction you need. Does anybody style with restriction? There's a restriction on B that's necessary. Remember, it's important that these matrices are invertible. B is not 0, right? Because if B is 0, then one of the eigenvalues is 0. The matrix is invertible, right? But anything else goes. So there's 20 possible characteristic polynomials for the matrix to be invertible, right? Overall, if you assume it's monic, there's 25, but 5 of those correspond, 5 possibilities correspond to a invertible matrix. Okay, so if we're going to list all the possible rational canonical forms for matrices here, we have to go through all the possibilities of varying factors, right? So I want to give you the invariant factor types. We'll figure them out and then see what kind of matrix it corresponds to. One of the things I could do is I could have you can have a double root. Everybody agree with it? And what's the restriction I need on A? It's just not 0, right? Now this breaks up into 2 subcases because A, 1 invariant factor, x minus a squared, which is a squared minus 2a. The matrix that I get from this, for the form of matrices, is this. Zero, 1, minus a squared, 2a. And I'm going to write a 4 here because there are 4 different conjugacy classes, 1 for every value of A. Agree? So there's 4 like this. What's the other case for this? Well, you'd have 2 invariant factors. X minus a, x minus a. And this and again, you got 4 choices for it. By the way, it's clear in this one, if you choose A equals 0, then it's C. So far, I've collected 8 conjugacy classes. 4 like this, and as you run through the values of A that are not, values of A in Z5 that are not 0, you get 4 conjugacy classes, and 4 like this, including, notice the identities, and this is one of these. Okay, what else? Well, 2 characteristic polynomial is x minus a, x minus b, a, b not 0, and a, b distinct. By the way, notice that this is for this one, since these two are relatively prime, there's only one invariant factor, and here it is. And by the way, how many equivalence classes should this be? The question really is, how many polynomials, how many distinct polynomials looks like that are there? A, B are not 0, and A and B are different. Okay. You're picking from 4 things, 1, 2, 3, 4, because you got to pick from non-zero things, and you're picking a set of 2 of them. Right, so this should be 4 choose 2. So there's 6 equivalence classes right there. Okay, I think we've exhausted. Basically, what we've done so far is I think we've exhausted everything where you've got roots in Z5, right? You got the double root, you got a pair of different roots. What's the alternative? Well, finally, your characteristic polynomial might have no roots whatsoever in Z5, right? So where do I get this? Notice in a field of characteristic 5, you also have a quadratic formula. Right? The quadratic formula basically works whenever you can divide by 2, right? How do I tell if this polynomial is reducible or not? Basically, y'all remember the discriminant, the stuff that goes under the square root. Irreducible if and only if the stuff that goes under the square root is not a square. I think actually I got something like 10 possibilities for this. and- So, of course, you can't pick, again, you can't pick beta equals 0, right? And once you pick, so you pick your, so you could pick alpha equals 0, but for any value of beta, you just go through this. And I think you get a grand total of 10 equivalence classes here. And what they'll look like, looks like this. Everybody okay with it? Let me also point out a couple of things before I 86 this example. The first one is I'm only doing rational canonical forms here, stay consistent, but I can also do this one, for example. This one's like a little bit wonky, right? I mean, it's kind of ugly. I can also do this one in the Jordan form, right? Because look back in this case here, one invariant factor looks just like this. So an alternate, this would be that. Right. Okay. There's an easier alternate for this one too. So this is the Jordan canonical form, gave me an easy alternate for this one. Anybody see an alternate for this one? Well, here I use the invariant factors, right? I could also use elementary divisors, right? And since A and B are different, then I have elementary divisors like this. So my elementary divisors are x minus A and x minus B, which makes for easy one blocks. This is the primary rational canonical form. Turns this one into something easier. Now for this one, I don't think it gets any better because the problem with this one is you don't have the roots down here, so you're going to need something like a rational canonical form to compound this. But notice that most of these turn out to be easy. I can write this one here, this one like this, and this one like this. By the way, here's a fun thing for you to do. What's the order of this matrix? Right. It's whatever the order of A is, right? So if A is 1, it says we're 1. If A is 2, the order of 2 in Z5, 2, 4, 8, which is 3, 1 is 4. So if it's 2, 2, it's a order 4. If it's 3, 3, it's a order 4. If it's 4, 4, it's a order 2, right? What's the order of this one? It's the least common multiple of the order of A and B. So the order of that one's either going to be 2 or 4. How about the order of this one? This one depends more on the beta and the alpha. I found one of these of order 24. This one's kind of bigger. What's the order of this one? Well, let's look at that one. Let's see order of an element in that conjugacy class. If you look at A10A, A10A, I think you'll see the pattern pretty quickly. This is A squared 2A 0 A squared. Correct. And A squared, 2A, A squared, A10A is A cubed, 3A, 0, A cubed. Everybody okay? Y'all see the pattern? So if you look at A10A, the fifth power, this is A to the fifth, 0, 0, A to the fifth. And A to the fifth is A modified. So now to go from the fifth power up, you just need to take it to the order of A power. So the answer to this, the order of this one right here, this is equal to 5 times the order of A. Right, so it's either 5, 10, or 20. Right. Well, like I said, one of the other ones that I got that you really need right from canonical form for, I got an order 24, and you can go through and figure all that stuff out. So you can really use this to kind of take apart what the elements of this group. Okay. Any questions? Okay. Now it gets exciting even more. Fields and Galois. So I'm going to start off talking about field extensions and kind of some of the basics about field extensions. So one way that, so here's kind of a quick, now that you have a background in all this stuff, a quick way to define a field is it's a set, non-empty, two operations on it, right? The first operation I'll call addition. The field is an abelian group under addition, and it is an abelian group. When you remove 0, it's an abelian group under multiplication, and the distributive property works between two operations. So from the point of view of ideals and stuff like that, fields are boring. A field is a commutative ring of identity such that 0 is a max element. So in particular, 0 is the only proper ideal of this. So it's really not too exciting from the point of view of ideal theory, but it's very rich in looking at the units. So let me point out some basic field stuff. A field always contains field always contains an element that's the identity, multiplicative identity, that I consider to be distinct from the additive identity. I don't want to call 0 in the field. And from now on, I will just usually say 1 instead of 1 sub f. Now, there is a big kind of distinction here. 1, if characteristic field 0, then Z is contained math. Because what that means is the additive order of the identity element is infinite. And so you have an isomorphic copy of Z inside the field. Therefore, Q is an So in other words, Q in a certain sense, isomorphism, is the smallest field. All right. So if you have any characteristic zero field, any field characteristic zero contains a copy of rational numbers. Here, the characteristic of F is equal to n bigger than 0, then n is looking, must be true about n. That's right. And n is prime. And I'll write n equals p because I can't stand to write n for prime. And the field contains Z mod P, a copy of that. That is Z mod P and not the P at X, of course, because it has to, because actually the entire field, for the rational numbers, to get the rational number from the integers, you have to take fractions, but you don't for the finite field, because everything, it creates its own inverse magically as it goes along. So this is called isomorphism. If field characteristic 0 then map of isomorphism, characteristic of that then ZP. And these are called prime subfields. They're truly smallest, and you can realize this is the intersection of all. Take F, and you can realize this is the intersection of all subfields of F. Okay. Now let's go on. There's an important notion in field theory, and it's called extension fields. So a field K is said to be extension field of F if F is contained in K. Simple enough, right? K is an extension field. It's a bigger field that contains F inside it somehow. And let me point out that K is an F module, right? Because actually, if you have any extension rings R inside T, the bigger ring is a module of the small one. F is a K module, but F is field, so K is a vector space over F automatically. And the dimension of K as a vector space over F is denoted with column F. If E is a field such that E is between F and K, then E here's Q is a field extension of rationals. R is intermediate. Here's a couple of things to kind of tip you fancy. Number one, does anybody know what the dimension of C as a vector space over R is? So what do you know about complex numbers? What's the first thing they tell you in complex numbers? A complex number can be written as x plus iy, a plus ib, uniquely. That makes 1 and I a basis for the complex numbers of the reals. So it's what's the dimension of reals with Q? Very big. In fact, it's actually uncountable, as a matter of fact. It's interesting to note that there are no intermediate extensions. The degree of this extension is 2. There's nothing in between, right? The degree of this extension is very big. And there is, can you name a field in between Q and R? How about I'm going to make this more formal later. The smallest field contains Q and I. Oh, whoops, that didn't work. It's not hard. How about this? There we go. How about that? That'll work. By the way, can you name something between Q and R that is not a field? There's actually many. Very good. Right. This is actually a ring because pi inverse is not in here. This is the smallest ring that contains Q and pi. We'll prove this later. Notice the smallest ring that contains Q in radical 2 contains 1 over radical 2. Because, well, you might tell me why. If you have the smallest ring that contains Q in radical 2, you also have to have the inverse of radical 2. Because you can just take radical 2 and multiply by 1/2. And now you've got 1 over radical 2. The difference is here, the way I can get away with this is pi is not algebraic. It's the root of a polynomial, where radical 2 is. And we'll make all that a little bit more on concrete later. Here is a theorem. Let F inside E inside K be fields then so the degree of K over F is the degree of K over E is the degree of E over F. This is important for many reasons. This comes up in a number of theories all over the place. Let me give you a quick application.
This was on our matrix exam. This is like the first problem last week.
Oh, this?
Yeah, but with respect to obviously, vector spaces.
Right, right.
Which
And
is-
that's essentially what it
is,
is, right?
so.
Did you have to do it for any basis, or did you assume finite?
Finite, yeah. So.
We will not assume finite, so I'll go further, but I mean, in the spirit, it's the same. Let tornadoes of P be e to the 2 pi I over P. This is a primitive pth root of unity, right? This is very important in number theory. And in fact, so I'll give you kind of a little history as we go along here. In fact, Z is to Q, there's an analog up here. And actually, these things can be complicated, but in this case, it's rather simple. Z is to Q is Z adjoint, this thing is to this pair. Now, Z has the fundamental theorem of arithmetic, right? In Z, you take every non-zero non-unit and you can factor it uniquely into primes up to units, correct? Does this have the same fundamental theorem of arithmetic? The answer is not always. If this did have the same fundamental theorem of arithmetic, if this had unique factorization the way Z does, Fermat's theorem would have been solved in 1847. It was a long time ago. And there was a proof given for this, assuming unique factorization. And it works for a while. The first prime that this fails for is 23. And then it starts failing a little bit more. And historically, for Fermat's theorem, they then patched this case when you didn't have unique factorization. It turned out that there's something called the class number, and if the class number wasn't divisible by P, or right, if the class number didn't divide P, then you could also do that well. And they call those nice primes, they call them regular primes. And of course, Fermat's theorem has been solved, but I think they defined regular primes too early, because the last I heard, it is known that there are infinitely many irregular primes. It's not known if there's infinitely many regular primes. So that is certainly a case of premature nomenclature. So in this extension here, it turns out that the degree of this extension is prime. I've been saying right here, is prime. And so what that means, something that's actually kind of cool. And that means that there is no other field properly between here by this theorem here. Because if you have an intermediate field E, then the degree of big thing over E or middle thing over Q, one of these has to be 1 because the total degree is P. So there is no proper intermediate field. So that's kind of a nice application. So let's see how far we can get into this proof here. So let U the set of UI be a basis of E over K, basis over, I'm sorry, E over F, and we need a basis for now what we want to do is, this is quite a surprise here. So look at all possible products as you run through both indices. you want to show that, need to show X is a basis over K over. Now spanning is not too bad because let K let K be in K, then we can write K as 1B1 plus E2 B2. By the way, I'm not really respecting my other indices, but forgive me for this. I'm sort of, because these index sets may be uncountable or something like that, but I can certainly pick a finite number of these out of my these here and write K this way. And of course, by the same token, each EI we can write as I can write this as AI1U1, AI2U2, MUN. And of course, some of these coefficients can be zero. I assume that I picked M so large that I assumed every possible value that I would need for expressing this with AI J in F. And so in particular, so X spans K over X, being around the herd, because y'all see what we do, right? For each EI, we replace the EI with this, multiply the VI through, and basically you get the K as a linear combination of the EIs. Okay. And let me see how quickly we can get linear independence. Let's assume sum Rij UIBJ equals 0. I'm going to rewrite the sum as the sum over J, sum over I, Rij. Just rearranging this. Now, because of the linear independence of the VJs, each one of these, Rij UI 0. But now, because of the linear independence of the UIs, right, these are linearly independent of F. Right. So when we rewrite it this way, these are all elements of V, or I'm sorry, these are all coefficients here, and the coefficients all have to be 0 by the linear independence of this. And now that you pull this out, each one of these is a linear dependence relation, which means that all the Rij's are 0. Right, okay. And so now what we have is the cardinality of X is equal to the cardinality of I cross J, which is cardinality of I times cardinality of J. So this gives what I want. Degree of K over F, degree of K over E, degree of E over F. Only actually I should probably reverse these two. Okay, any questions on it? Questions? How about out there? Any questions? Well, think about rolling by the math club. If you have time today, it should be a good talk.